Hey there, everybody, welcome back. We're doing 8.4. You love how I just like treat it like we're not continuing from the previous lecture for people watching it later on. 8.4 is on algebraically defined vectors. And something called the dot product. Dot product is also has another name, it's called the inner product. And you'll see why in a second when we get to that. Now, in point 8.3, we had talked about a little bit. Treating U as a vector. Writing it with like A comma B. This is a vector that starts at the origin. And ends at the point or coordinate AB. Which means it has, if I made a triangle, the x component or this length here is A, because x equals A. And the y component or the height would be B. Now, even though we just got done talking about some problems in the previous section with bearing and shit like that, normally our angles are off the x-axis. So if I have an angle theta there, we have that. And this is my u vector here. Since what I have pictured are lengths though, A and B are lengths, I'm gonna write this with the absolute value looking things on them. And just like when we did the unit circle. And we said x was r cosine theta. And y was r sine theta. Well, here r is the magnitude of u. So that means my x equals r cosine theta, here turns into pictorially a equals magnitude of u cosine theta. And y equals r sine theta, b turns into the magnitude of u sine theta. So I could write u as the magnitude of u cosine theta, magnitude of u sine theta. Well, we'll go A, B, just see them together. What is that magnitude though? Well, it's a length. And we can use Pythagorean formula, right? A squared plus b squared equals magnitude of u squared. So magnitude of u has to equal. Take the square root of both sides. Normally, when we take the square root, we have plus or minus. But we're talking about lengths. So only this one applies. Lengths have to be positive. You will hear sometimes magnitude of u is also called the norm of u. What is theta here? In terms of these A and B components? Cause that's usually what we're gonna have, we're gonna have the coordinate where it ends up. That's kind of like what we wanna base our shit off of. Well, if we look at the triangle. Looks like theta is opposite over adjacent. That's tangent. So tangent theta is B over A. So theta is tangent inverse of B over A. This gives us an effective way of rewriting AB in terms of AB and the angle. So let's find the magnitude. Uh, 6, -8. And angle. So we can rewrite it in terms of those. If it helps, draw a picture. A reference angle would be this. So this will be, this is our magnitude. And that's the hypotenuse, so 6 squared plus -8 squared equals magnitude of u squared. (36 plus 64), which is 100. Which tells us the magnitude of u is 10. If I want to find theta. I don't think of this in terms of tangent inverse, I really don't. I always switch to saying tangent theta is opposite over adjacent. And then taking the inverse. If you jump straight to the inverse, more power to you. My brain don't operate like that. Okay, theta equals. Well, approximately -53.1 degrees. So we could say this is 10 cosine of -53.1 degrees. 10 sine of -53.1 degrees. But this is not the optimal form. Kind of don't want the negative angle in there. One option you have is to figure out what the actual angle was. The actual theta is doing this. So. Theta plus theta hat equals 360. So theta equals 360 degrees minus the 53.1. Which is what, 306.9? Yeah, we could put 10 cosine of 306.9. 10 sine of 306.9. That works. This works. But there's something better. Cosine theta is an even function. Which means cosine of theta or negative theta is the same thing as cosine theta. Sine is odd. So sine of negative theta is the same as negative sine theta. So instead, I could write this as 10 cosine, use the positive 53.1 degrees. And then sine, we got a negative, I'll pull the negative out. That's probably the best form. Or readability. This one, the one in red. This one will allow you to definitely find 6, -8 again. you can like pictorially see it from the angle. When we switch to this, we'll still get the same values. If we do this, we're still gonna get 6, -8 when you plug and chug. But this form is a little bit easier to see. We're rotating 306, it's really what it's saying. Rotate 306.9 degrees and then go a length of 10. This format right here is gonna come up more near the end of the chapter. This is tend to be what we're gonna call polar coordinates. Or use the actual exact value for the angle rather than using even and odd function. This is later in chapter 8. These are a vector. When we write in polar coordinates are not vector form. Polar coordinates, kind of like we have like x comma y. Polar coordinates are r comma theta. So for this problem, it would be 10 comma 306.9 degrees. And usually theta is in radians, but it doesn't have to. This is not a useful problem in radians. But like I said, polar we're gonna hit later. Here we went from having the xy coordinates to the magnitude and angle. Now let's go the other way. Let's start with find the coordinates. For values of x and y. Of a vector v. With a magnitude of 14.5. And a direction angle of 220 degrees. So 220 is past 180. That's 180. I need to go another 40 degrees to get to 220. So that'll be the 220 angle right there. All of it. And this has a length of 14.5. We are looking for the x value and the y value. So we can use the magnitude. Remember, it's the magnitude times cosine theta. Magnitude sine theta. For our coordinates. For this. That is 14.5 times cosine of 220. 14.5 times sine of 220. Take a break right after this one. I am getting negative 10.7. And -9.3. Now, we can take a break, but I'm gonna give you some examples to work on for when you get back and you're ready, go over when you're done. Write each as. In the form. A, B. We'll do one is magnitude of 8. 135 degrees. Magnitude of 4. 270 degrees. And magnitude of 10. 340 degrees. Alright, we wanna go to the other form, we gotta do the magnitude times cosine. And the magnitude times sine. This is -√2/2 and +√2/2. So the simplest form of this is gonna be -4√2. 4√2. That's the exact form, if we want an approximation. About -5.66. This one will do 4 cosine of 270. 4 sine of 270. Which should get us 0, -4. And this one, the only cleanest form, the exact form that's gonna be correct. Is gonna have to keep it. Is that. This would be the exact form, oops. That's exact. And then if we want an approximation, we can find that. Should probably only use one, but. The accuracy is all dependent on what you're using for. If I start rounding shit too much, people are gonna assume that's okay in general form. And should be rounding appropriate to what you're doing.
I thought we should maybe go one farther. Because it's
We
three,
could have gone one farther,
but it's also,
but like 10 is only one significant digit, really. The 0 doesn't count. So the correct rounding would be downward. Alright, we already talked about the vector algebra of all this. But I will rewrite it as a reminder. If U equals AB. And B equals CD. Vector U plus vector B is gonna be A plus C, B plus D. You add the x values. Same thing with subtraction, we subtract the values. We talked about scalar multiplication, k times u. Is gonna be k times a, k times b. You can just move the multiplier inside like you're distributing. Now that looks like an 8, Jesus. But let's give you some practice, we didn't really do a lot of practice with this. Let's say u equals 6 comma negative 3. And b equals negative 14, 8. Find u plus v. One half v. And 5u minus 2v. Try to work that out, and we'll do it together. Six negative 3 plus negative 14, 8. Negative 8, 5. This will be 1/2 times negative 14. 1/2 times 8. Should be negative 7, 4. So if I do 5u, I have 5 times 6. 5 times negative 3. And then I'm gonna write this as a plus and move this negative 2 in as a multiplier. So negative 2 times negative 14. Negative 2 times 8. This just helps me turn into addition where I'm not potentially fucking up signs later on. I've got 30 negative 15 plus 28 negative 16. Looks like 58 negative 31. There we go.
You can write the middle set as with multipliers in the inside of like next to the numbers, like if you eventually write it as 5 times 6 plus or plus negative 2 times.
Yeah, you can do, I can combine them before doing the actual,
That's all.
yeah. You're gonna see that you get the same thing. They'll get you that. You ready for more? Alright, when we have a vector with a length of 1. Magnitude of 1. Are called unit vectors. Like unit circle is a circle of radius 1. The two most common ones are in at least 2 dimensions. I is 1, 0. We call this. Generally it has a hat on it. I hat. And J hat is 0, 1. You'll see if you do the magnitude of these, you've got 1 squared plus 0 squared equals 1. This means any vector AB can be written as A times 1 comma 0 plus B times 0 comma 1. Which is A times I hat plus B times J hat. Alright. We'll take advantage of that kind of stuff in a second, after we talked about the dot product. So for this, U is still gonna be AB. V is still gonna be CD. The dot product or inner product. Has a dot between them. Inner product comes from how we see what happens. If I have A comma B. Actually, I'll do it here. A comma B multiplied by C comma D. What this turns into is A times C. B times D. But not really. It's no longer a vector. It loses the vector form. This is not a vector, it's a scalar. Oops. Just multiply the two x's, multiply the two y's. And that's why they call it the inner product. It's the product of the inner values. Now, there will be a form of vector multiplication that does produce a vector. It's called cross multiplication, but I don't think we cover it in PreCalc. It's a calculus topic in general. Because that's where you're gonna use it. Calc 3 even, not Calc 1 or Calc 2. So let's do some practice, finding the dot product of some things. Let's do -5, 2. Dotted with -2, -4. And then we'll take a look at 10, -1. Dotted with 1, 10. Here we'll have -5 times -2. Plus 2 times -4. Ten plus -8 is 2. Here we have 10 times 1. Plus -1 times 10. 10 plus -10 is 0. This actually arises in a special situation that we'll talk about in a second. Oftentimes you will see this being read as U dot V. That's how people read it. So if I say U dot V, I'm talking about the dot product. I could say the dot product of U and V, but that's a really long way of saying U dot V. You know what I mean? Three-dimensional, in fact, we'll do three-dimensional right now. It will actually help with let me do the first part, 2 dimensions, then we'll switch to 3 dimensions. Let's look at like, how does this come about? We had U was AB. B was CD. And I can write this as U equals. A I hat plus B J hat. And this is C I hat plus D J hat. So when I'm doing U dot V, I'm really multiplying these. So I get A times C times I squared, or the magnitude of I. Plus A times D, I times J. Plus B times C. J times I. Plus B times D. J dot J. Yeah, that's how we say magnitude of J squared. So when we have a vector times itself. Is written as magnitude of U squared. So magnitude of I squared, we already talked about this, the magnitude of one I was 1. And J, it had a magnitude of 1, it was a unit vector. What is I times J and J times I? One zero times 0 1. Is 1 times 0 plus 0 times 1 is 0. And the same thing happens with J dot I. Zero 1 times 1 0. 0 times 1 plus 1 times 0 is 0. So these cancel out. These are zeroed out. And we see that we get U dot B is AC plus BD. Alright, so Davis was asking about 3 dimensions. In 3D. I hat is 1 0 0. J hat is 0 1 0. And this is like the XYZ coordinate system. K hat is 0 0 1. What were you asking me about it?
I thought initially that what we had saw there since 10 minus 10 plus 8, I think 0, maybe there was that, there was an unseen like form of backlight.
No, this is not making a vector.
Yeah, there will be like back motion.
The cross product actually does make that, it makes a vector that is. The cross product, when you do it in Calc 3. If you have 2 vectors like this. It makes a third vector coming out of the page. If you go this cross that, if you do this cross that, it's going into the page. But that's Calc 3. I do not wanna take you down that rabbit hole. Let's talk about the different things that we see if we look at all the different forms of dot product here. So we will find like the properties of the dot product. First one, U dot V is the same as V dot U. You will find most of the rules that we know about arithmetic apply. If you just think of these things as multiplication. 3 times 4 is the same thing as 4 times 3. The dot product works the same way. We have, this is like called the commutative property. All the properties you know of real numbers apply. The associative property is U dotted with V plus W is the same thing as U dotted with V plus U dotted with W. That's the distributive property. The associative property has it set up like this. Remember, these values end up turn into a scalar. So it's not like a dot product between U and the parentheses. You do one set of dot product and then that outcome is a number, not a vector, and you just multiply. Interesting one is. K times the U vector dotted with the V vector. Is K times U dotted with V. K is just a multiplier. Which means the multiplier can instead be applied to that one. And we can have this is the same as U times KB. Or dotted with KB. I wrote A and then you have a giant fucking list of them. I don't even know why I said B at this point. I don't even need the A since I wasn't fucking labeling them. We have the 0 vector dotted with anything. In real math, what's 0 times anything? 0. Since it's the dot product though, it's now just 0, not the 0 vector. Textbooks, oftentimes they will use, this is worth noting. Textbooks often don't show the arrow. But boldface. To show a vector. That's really awkward when you've got 0 and 0. Looking at this without arrows on it, you gotta make that 0 look pretty fucking thick. To distinguish from the other 0 and recognize that the outcomes are different. And the one I mentioned earlier is u dotted with u. Is. The magnitude squared. You can see this when we had u equals AB. So. U dot U. Is AB dotted with AB. Which is A squared plus B squared. But the magnitude of U. Was the square root of A squared plus B squared. Which means that is the magnitude of U squared. The other form of the dot product. Requires a picture. So if I start with a vector U. And I have another vector V here. The vector going from here to here. Is. Let's see, I'll do this right. That's like. If I were adding them. U plus V is like this, would be longer. If I don't know what that is, I can do the vector addition. B plus C has to equal U. Because the tip to tail is how we add vectors. I know that one. We add vectors to get the U plus V vector. So the C vector is the U vector minus the V vector here. Let's say I had an angle theta here. Between U and V. If I use that, I can use the law of cosines here. So I've got the U minus V vector is my C vector, and we're squaring it. Law of cosines in this form, we're doing the magnitude squared. Equals the magnitude of U squared plus the magnitude of V squared. Minus 2 times the magnitude of U times the magnitude of V cosine theta. Let's look at that left side a little bit better here. This is U minus V squared. Another way of writing that vector is like that. Which is U minus V dotted with U minus V. Which is U dot U minus U dot V minus V dot U plus V dot V. So the left-hand side cleans up into the magnitude of U squared plus the magnitude of V squared minus two U dot V. Because remember, U dot V equals V dot U. So we combine them. That's my left side. My right side is still magnitude of U squared plus magnitude of V squared minus two magnitude of U, magnitude of V, cosine theta. Looks like we can subtract U squared and V squared from both sides. And cancel on both sides. And we get negative two U dot V equals negative two magnitude of U, magnitude of V, cosine theta. And after dividing by negative two, we see another form of U dot V. U dot V is the magnitude of U over the magnitude of V. Why am I? There we go. It's not over anything. That looks awkward. I'm just gonna rewrite it. Which gives us a new way of finding theta. Cosine theta is U dot V over the magnitude of U, magnitude of V. Where theta is the angle between U and V. It's handy because it gives us an easy way to find the angle between them. Rather than trying to do all that triangle bullshit. Wasn't that triangle bullshit a lot of fun? Like this is just multiplying and fucking dividing and shit. Rather than trying to have to do some obscure fucking sketching and geometric reasoning. We just have a formula for finding the angle between them. That's pretty nice. Before we do an example, I do want to show one other thing with this. What if theta equals 90 degrees? U dot V equals magnitude of U, magnitude of V, cosine of 90 degrees. Is 0. If the dot product is 0. Vectors are perpendicular. And for some reason, they've added a new word to this for vectors. Perpendicular tends to be for just lines. The same concept, perpendicular in terms of vectors. Is called orthogonal. So orthogonal vectors cross at 90 degrees. So back when we did 10, 1 and negative 1, 10. We saw that was 0. If you kind of sketched it. 10, 1 is over there. Negative 1, 10 is right there. We did the angle between them, it's making a right angle right there. So, let's find. Real quickly, just for a little bit of practice, find the angle between. 5, negative 12. And 4, 3. Yeah. 20 minus 36 on top, which will clean up. This one here is the square root. 25 and 144 is 169, that is 13. And this is 16 plus 9 is 25. Square root of 25 is 5. 13 times 5 is 65. This is negative 16 over 65. So theta will be cosine inverse of that. So when you're doing this. If we've got U and V. We have two angles we could look at, we can look at this angle here. Or we could look at the angle going all the way around. Theta is always the inner angle. Which means theta is always between, when we're doing it like this. 0 degrees and 180 degrees. If cosine theta is positive, you have a less than 90 degrees. And if cosine theta is negative, it's greater than 90 degrees. We're not doing like negative theta and negative degrees. It's gonna be something where you have a angle larger than 90. And that's 10 o'clock. I gotta wrap it up. GTFO. Have a good day.